The next speaker is Geva from the Technion. He will talk about X-ray computed tomography through scatter. This is a joint work with Yoav Schechner, Yonatan, Chernyak, and Rajiv Gupta.
Okay. So let me start with a question. How many of you have undergone a CT scan? I can't see you very well, but I believe many of you have. CT scans are widely used. They were introduced in the 1970s. There were 3 million CT scans that were performed in the US in 1980, and this year there were over 80 million scans, and this number is still increasing. Today it is considered the #1 man-made source of radiation that is affecting us. The effects of this radiation on our chances and on our likelihood to develop cancer is still a very active field of research and debate. CT is also a life-saving invention that has deeply influenced the way medicine is conducted today. It is used in management of many medical conditions, such as tumor detection, skeleton injuries, strokes, traumatic brain injuries, and many more. However, it is still far from being optimal and involves many radiation risks. We believe it can and should be significantly improved, and this can be done through scatter. So, how does a CT work? An X-ray source and an X-ray detector are mounted opposite one another in a circular gantry. The patient is positioned inside the gantry, while the source and detector rotate around them, collecting measurements from different angles. This is how it looks in real life. At full speed, one rotation takes 1/5 of a second. Just imagine the engineering complexity of this machine. The traditional circular shape of a CT is not necessarily the best fit for our human shape, right? An elliptic shape would fit better. It would be more compact and would also enable to reduce the radiation when projected along the minor axis. However, do you think this is possible? Let's focus again on the traditional setup. When the source is active, X-ray radiation flows through the imaged object before hitting the detector. Some radiation passes uninterruptedly and gets recorded at the detector. Some is absorbed by the object. Some is scattered away from the detector and hence completely ignored. And some is scattered towards the detector. The radiation that is scattered towards the detector is blocked by a designated hardware called anti-scatter grid. An anti-scatter grid is made of strips of lead, as seen here. Its purpose is to ensure that only the directly transmitted radiation that passed with no scattering from source to detector is recorded by the detector. The scattered radiation is blocked by the anti-scatter grid. And also, because the anti-scatter grid has a finite fill factor, it also blocks some of the direct transmission. In current CT, around 50% of all incident radiation is scattered by the body. Think about it for a second. This is ionizing, cancerous radiation that traveled through our body, may cause damage, and scattered away from our body, but it carries information. Today, it is simply rejected. This wasteful mechanism requires much higher levels of dose than necessary. And you know why are the scattered photons being rejected? Because of a simple mathematical model that is in use since the 70s. Do you think this is justified? We don't. So another thing about the anti-scatter grid, it has to be aligned with the source, which then dictates this complex rotating mechanism. Let's go back for a second to the desired custom scanner shape. Ideally, it should also be entirely motionless. This would mean that we can remove the rotating mechanism, reduce the cost significantly, make it portable and also more accessible to patients in emergency situations. And this can be achieved by having a complete ring of detectors and a complete ring of sources surrounding the patient. The sources can then be switched on and off sequentially, virtually executing rotation. However, in this setup, an anti-scatter grid would be only useful for one projection angle, occluding the rest. So an anti-scatter grid cannot be used in a motionless setup. So let's recap what we know about the anti-scatter grid. It causes much more dose to the patient. It forces alignment to the source, which then dictates this rotating mechanism. And it restricts to traditional circular shapes. However, if we remove the anti-scatter grid, which is exactly what we're about to do, we have indications that we can bring down the dose by up to 5 times. We can open the way for development of motionless CT scanners with custom shapes. So the obvious question is, with all the benefits of not having the anti-scatter grid, why do we even have it in the first place? And the reason lies in the current method of reconstruction, which is called linear tomography. Remember the simple mathematical model that I was telling you about earlier? This is exactly it. In linear tomography, a ray is attenuated between an X-ray source and a detector. The measurement is an integral of the body attenuation mu along the ray. The goal is to estimate the spatial distribution of mu. The object is discretized into voxels of constant mu. The measurement of ray R is IR. How is IR formed? This is voxel J with value mu J. ARJ is the length of the intersection of ray R with voxel J. Then the value of IR accumulates along the ray, as shown here. Or in matrix form, all values of mu are stacked in a column vector, values of the intersections in a row vector, and IR is the product. And having multiple sources and multiple views, we get a set of linear equations arranged in a matrix form. In blue is the vector of measured signals from all detectors in all views. In green is the unknown attenuation per voxel. Matrix A represents the line voxel intersection segments. And this can be done using common optimization methods that minimizes a cost function with some prior. Now, as you can see, this is a simple model, but it assumes only straight rays from source to detector and no scatter. So far we understand that linear tomography is where trouble begins. It assumes direct transmission, which requires anti-scatter grid, which then leads to very high dose and a complex rotating mechanism. But if we remove the anti-scatter grid, we have indications that we can perform reconstruction with up to 5 times less dose. We can open the way for development of motionless setups, and we can do more than that. We can also do chemical decomposition, which we will talk about shortly. However, now we need to account not only for the direct transmission, but also for the scatter signal. But the way we look at it, scatter is not a curse to overcome, but a blessing. We're accounting for it computationally. This turns the tomography into non-linear anymore, which is complex to compute. But luckily, strong computers are available today, so we believe it's no longer justified to keep using the methods of the 70s. Regarding prior art, most deal with scatter as nuisance, trying to reject it or avoid it. We exploit scattering as a source of information. There are scattering tomographies in visible light, say to recover clouds. However, their scattering is elastic, and I will explain what elastic means in a second. We deal with X-rays, where both elastic and inelastic scattering exist. There are also works that exploit inelastic scattering as a source of information, but they do it in the high energy regime using gamma rays, and they assume only single scattering. We deal with medical X-rays and have no limitations on the number of scattering. So our work facilitates a setup having multiple sources and multiple detectors that collect measurements simultaneously all around the ring. We have no anti-scatter grid, and we have a strong scatter component in our measurements, which we account for computationally. And how do we do it? We define a new inverse problem. It is based on a forward model. The forward model takes a representation of materials denoted gamma. It also takes the geometrical setup and the source and detector properties. Given these 3 inputs, the forward model I produces projections, including scattering, as measured in each detector per source. Scattering tomography, as we define it, is solved by optimization. With the ability to calculate the forward model I, we want to find the optimal material distribution, volumetric material distribution, gamma hat, that minimizes the distance between our scattering model I and the measurement, as seen in all detectors from all sources. And for this, we need to first formulate the forward model and solve efficiently. But let's pause for 1 second and discuss a phenomenon that is familiar to many of you: haze. In the attempt to perform dehazing to an image, the principal model in computer vision has several assumptions. That the light scatters only once on its path from the sun to the camera, that scattering does not occur inside the imaged object, and that the light maintains its wavelength throughout. There are lots of similarities between the model of dehazing and our model. Like in haze, an X-ray photon can get absorbed in the medium. Like in haze, an X-ray photon can also scatter elastically in what's called Rayleigh scattering. But there are also lots of differences. For example, in haze, in our model, scattering is not elastic, which means that the photon can change its wavelength. And most importantly, the dehazing model treats scattering as a disturbance, while we use it as a source of information. So as I mentioned before, we have also inelastic scattering. And this is called by Compton scattering. Here is an atom. An X-ray photon hits the atom and frees an electron from the atom. The atom then becomes ionized, which may mean damage to tissue. The photon continues on a different direction with a longer wavelength, and this is exactly inelastic scattering. So our forward model needs to account for all possible photon paths as they interact with the imaged object. Let's see some examples. A photon can travel freely until hitting the detector with a certain final energy E path. A photon can also get absorbed in the medium. A photon can undergo Compton interaction, which will then lead to a wavelength shift and a change of energy. And later on, it may undergo more interactions, for example, Rayleigh interaction that will maintain its wavelength before hitting the detector. And of course, there's no limitation on the number or type of interactions that a photon may occur and may undergo before hitting the detector. So let's summarize the forward model. There are three dominant interactions: absorption, Rayleigh scattering, and Compton scattering. Each of them has a certain probability of occurring, P. This probability depends on the photon wavelength, on the density of the volume ρ, and on the chemical composition. Note that Compton scattering causes a wavelength shift, which then alters the probabilities of the next interaction. We recover the chemical composition in every voxel and the density. So our unknowns in each voxel V are the mass concentrations of elements in that voxel, which means, in simple words, how much oxygen, how much calcium, how much hydrogen exists in that voxel. Gamma is the matrix of all concentrations in all voxels. This is what we try to recover. And why are we sensitive to the specific elements? Because the elements differ in their scattering characteristics. For example, here you can see in the top plot elements that are most common to human tissue. For example, hydrogen, oxygen, calcium. And you can see the relation between Compton and Rayleigh scattering for these elements. The bottom plot shows you the angular distribution of Rayleigh and Compton single scattering when measured in a setup having detectors all around, and the object that was irradiated here was a volume with a single homogeneous material. So the idea is that each element has its own signature Rayleigh and Compton response, which depends on the element's characteristics. Calculating the forward model is done with Monte Carlo. This poses no limitations on the number of interactions or the photon energy. In Monte Carlo, for every voxel, the probabilities of interactions are calculated from the material characteristics. Then millions of photons are generated at the source and traced individually as they undergo interactions before hitting the detector. The final detector measurement, when projected from source S, is the sum of all photon energies that hit the detector. So we know how to calculate the forward model and the cost function. In order to solve it efficiently, we need the gradient of the cost, which depends on the gradient of the forward model with respect to our unknowns concentrations. And this is calculated as well by Monte Carlo. Again, we generate millions of photons and trace them individually as they undergo interactions in the volume before hitting the detector. However, here we sum over the segments of the path. For each segment, we calculate the cost function of the probability of that specific segment with respect to the concentrations in the voxels intersected by that segment. Now, I don't expect you to understand it from this one slide. I just want to mention the work by Yanis Gioulekas, from which we drew inspiration for this method. So we solve it iteratively, and in each iteration, we calculate first the forward model using Monte Carlo. We then calculate the gradient of the cost, again using Monte Carlo, and consequently we take a step according to the gradient direction. When using Monte Carlo with only a finite number of photons, the results are noisy. We then use stochastic gradient descent for the optimization. Note that the time complexity to calculate the gradient is the same time complexity for calculating the forward model. They're both done using Monte Carlo, which means that the time complexity is linear with the number of generated photons. We use for each iteration 10 million photons to calculate the forward model and 100,000 photons per source to calculate the gradient. Reconstruction of a volume having 100 by 100 by 80 voxels on our local CPU server took around 3 hours, which means it's soon becoming feasible for industrial implementation. We first tested our method in simulations. Using simulated CT setup and a realistic human phantom, which is called XCAT, we generate 2D projections. These projections have a strong scatter component. We then use our method and iterate to find the optimal reconstruction. So these results here show you a slice of a human hand through the z-axis. And you can see here the improvement as compared to linear tomography. And also, because we represent our volume from its material characteristics, from its elemental composition, and because each element has different scattering characteristics, we can recover more than just the density. Here, for example, you can see that we recover the chemical decomposition. So oxygen is dominant in all tissue, for example. Calcium is dominant mainly in bones, while hydrogen is present in the surrounding air. And we've performed another set of simulations, this time imaging a human thigh. We compare our method with different types of linear reconstruction. So here is an example raw measurement projection taken with no anti-scatter grid. Here is a reprojection from an object that was reconstructed in a traditional CT setup having anti-scatter grid. And this is a reprojection of a volume reconstructed by our X-ray scattering tomography, of course done with no anti-scatter grid. Note the small differences from the raw measurement, which points on the accurate reconstruction. We compare our method with linear reconstructions done with or without anti-scatter grid as a function of the dose to the patient. And as you can see here, our method was able to achieve the same reconstruction error with 5 times less the amount of dose. This gives hope for significant potential of reduction of dose. And it's not just a fairy tale. An actual motionless CT setup is developed by our colleagues. Rajiv Gupta is director of the X-ray imaging lab at Harvard Medical School. And they're actually building a prototype of such a motionless scanner. Using data from their scanner, we were able also to reconstruct a real object, a pig lung. As you can see, this is just a qualitative experiment because we don't have ground truth. Also, you can see that the differences between our reconstruction and the linear tomography is small, and this is because the imaged object here, this lung, is very small, only in the order of a few centimeters. And it also has very weak scattering characteristics. However, this shows feasibility of scaling our method to real data. And this is only our first research on this topic. There are many, of course, many potential directions here. For example, since we're facilitating a setup having multiple sources, it would be very interesting to think of smart illumination schemes where multiple sources are switched on at the same time. This may lead to further reduction of those. Also, we were using only simple energy integrating detectors, but today there are more advanced detectors that can also sense the energy of each photon that hit them. And generally, we believe that many of the tools that are used in traditional computer vision inverse problems can be adapted here to this model. For example, using smart priors, GPUs, of course, deep learning, you name it, and Yoav is looking for students. Let's conclude. Linear tomography assumes direct transmission, which requires anti-scatter grid, then leading to very high dose and a complex rotating mechanism. If we remove the anti-scatter grid, we have indications that we can reduce the dose by up to 5 times. We can also develop motionless setup and perform chemical decomposition. However, we need to deal with not only the direct transmission, but also the scatter signal, which turns the tomography into non-linear and complex to compute. But our X-ray scattering tomography can do it. Thank you.
Any questions? Okay.
Sounds exciting. Are you worried of the risk of local minimum?
The risk of what, sorry?
Local minimum.
Yeah, that's a good point. Of course, it's a non-convex optimization, and it's very highly dependent on the initialization.
Do you have a way to know if you arrived at a not good solution?
No, and it's a thing that we need to investigate. But at the moment, we're initializing with the linear tomography. So we're starting to iterate from this already quite good reconstruction. We then iterate from there to improve further. And yes, of course, we can hit a local minimum.
Okay, thank you.
Other questions? Okay, so let's thank the speaker again.